Welcome to Survey of College Math. I truly hope to impress you this semester at how useful this math stuff can be. And you know what? The more complicated it gets, and we're not going to get that complicated, but the more complicated it gets, the more personally practical applications are going to occur for you. So let's start off with something I know you know, and we'll build on that. And even today, we're going to get to something that's pretty practical. Well, let's see. Let's talk about the rectangular coordinate system and graphing. Okay, we know that we have really two axes. Okay, the x-axis, which has a 0, goes to the right in a positive direction and to the left in a negative direction. And of course, the x-axis on the rectangular coordinate system is joined by the y-axis, and it gets larger as you go up and smaller, or negative if you would, as you go down. Remember that? Now, as you see, it's divided into 4 parts. The first part, or quarter, or quadrant,
I know that, dude.
we call quadrant 1, which means we're going to have a quadrant 2, a quadrant 3, and a quadrant 4. Okay, so when I speak of a point being in a certain quadrant, hopefully you'll know.
Holy alphabet.
Like this. Hopefully you remember how to graph a line. We're reviewing today, remember. The first step that I always told you to graph a line, you got it. Solve for y. And it's going to allow us to use our calculator as well. So who's keeping y from being alone? That minus 2x. So I'm going to do the opposite. Add 2x to both sides. Both sides now. He'll go away. And let's see, I'll get 3y equals 6 plus 2x. Can't add those. Now I got to get rid of the 3. He's multiplying. So I divide both sides, the opposite, by 3. And I'll get, he'll go away. And finally I'll have y by itself. Y will equal 2 plus 2/3 x, or 2x over 3. Now in a problem like this, you may remember that I told you to put in not 0, 1, and 2. You could, but it's going to make life easier if you put in multiples of the denominator. Multiples of 3 in this case, because then you'll get rid of the fraction. Let's try it. Put in 0 for x, and nicely my formula for y tells me what y is equal to. In this case, y will be 2. And I'll graph that point. Go over none and up 2. Now let's put in a 3. For x, the 3's will cancel. That's why I chose 3. And I'll get 2 plus 2, or y is 4. I'll graph the point 3, 4. Go over 3 and up 4. Now I always tell you to do a third point just to make sure. So we'll use another multiple of 3, 6. Putting it in for x. It's nicely going to cancel, isn't it? Not completely. I'll get that 2. And then do your multiplication. 2 times 2 is 4, plus another 2. In this case, y is 6 also. So I plot the pair 6, 6. And I know I'm hunky-dinky because, look, they line up.
You look marvelous.
I'm not finished yet. I have to draw the line. And that is one way that we've learned up to this point how to graph a line, to solve for y and put in 3 points. There's going to be one more. I know I'm notorious for giving you only one way, but this is the big leagues now. I'm going to want you to know another way to graph lines.
I want to tell you my secret now.
This is a nice, easy way. Once you have something in, quote, standard form, looks like this, when the y and the x are on the same side, basically, we're going to use intercepts. Remember, if you would, or consider, that when x is 0, in the middle there, in the middle here, when x is 0, that's going to be the y-intercept. That's going to be the y-axis intercept. And we love 0. 0 is easy to work with. So let's set x equal to 0. It'll cancel that term out, and we can solve for y. Now, and we'll get y is what? Y is 2 in this case. So I guess the y-intercept is 2. Well, you can graph the point 0, 2 and see that. Now that's the y-intercept, where x is 0. The x-intercept is going to be where y is 0. Once again, we love 0. We'll put in a 0 for y in this case, and it'll be easy to work with. That term will cancel out. And we'll solve this time for x. Dividing by -2, I get x in this case is -3. And if I graph the point -3, 0, that is the x-axis intercept, and I only need 2 points. And I've graphed that line, son of a gun. It's another way, okay, possibly to use. Okay, I'll call that the intercept method. What about graphing quadratics? You remember this? Well, you can't just use, they're not going to line up. You may remember, I can't use that method. We have to use the vertex. Remember, the vertex was the middle of the graph, or the maximum or minimum. And the vertex always came, if the equation was of form ax squared plus bx plus c, it always came at the point -b over 2a. So in this case, let's see, -b over 2a would be -0, because there's no middle term, -0 over 2 times 1. The number in front of x squared is 1 in this case. So this one happens to be at 0, because that all comes out to 0. So the vertex will be at 0. So that's my magic number to put in first. I love 0. If I put in a 0 for x, I'll get 0 squared minus 2. I'll get minus 2. And I know the point 0, -2 is on there, but I know more. I know that it's the vertex.
I'm trying to think, but nothing happens.
Well, if I know it's the vertex, let me do 1 point larger than that. 1 point to the left and 1 point to the right. I'll start off with 1 point to the left. And let's use -1. If I put in -1 for x, let's see what I get. -1 squared is +1. 1 minus 2 is -1. So I'll get the pair -1, -1. I put 1 point to the left of the vertex. Now, let's do 1 point to the right of the vertex, which would be what? Would be +1 in this case. We put that in. We happen to also get 1 minus 2, or -1. So I graph the point 1, -1, and I can see where do you remember what this is?
Oh dear, that's too wonderful to be true.
I found out that it's a parabola. X squared is always a parabola.
That's the fact, yeah.
Any quadratic is going to come as a parabola that looks like a curve. Remember that? And you did it with only 3 points. You did the vertex, then you did 1 point to the left and 1 point to the right. Just a little review there, okay?
Now I use my secret weapon.
Let's do it with a calculator. What are some of the buttons on the calculator we're going to use here? Remember your buddy, the y equals? The x, I call that the x button. And the graph button, remember that? The clear button. Now that's the subtraction button. And that's the negative button, and they're going to be treated differently, so make sure you understand that.
Yoink.
And don't forget to turn it on, okay? Let's try it. Turn that baby on, and hit y equals. Now, you might have stuff from the last problem. I'll clear that out. Okay, hit clear, and type in what the equation is equal to. X to the second minus 2, or x squared minus 2. And cool as a mule, if you hit graph, you get it. Now, how do you erase that? You hit clear. Now, I'm going to try and do that with my calculator. Let's see. I'll turn it on. Okay. And I'm going to hit y equals. And I'm going to clear out the old work from last time. And I'm going to hit X. There's the X button. I use the to the button. To the second. I know you have this X squared button. That won't always work though. I use the to the second. And in this case, -2. So it's subtraction. -2. And if I hit graph, there's the graph. Of course, we knew that because we did it. And how do we get out of this? Clear. Great. Okay. Now I need you to be real experienced with this calculator.
How about a little fire, Scarecrow?
Let's do this one. Now,
I can do that, but I don't want to.
it's going to be quite difficult without a calculator, so let's use our calculator.
In a job for you know who.
Let's use the calculator just to get more practice. It's probably already on, isn't it? You're going to hit your y equals, clear out the last problem, because it'll remember it forever, and let's type in what it's equal to. Use your parentheses now, x plus 4 to the third. Remember, see, that's why I told you not to use the squared, because this way you can do the to the for any power. And if you hit graph, how cool is that? Do you remember how to erase it? You hit clear. Dare I try it? Let me bring up my calculator, and I'm going to hit y equals. I'm going to clear out the old one. There's the clear. And I'm going to have to use my parentheses this time. Remember where they are? And there's the x plus 4 parentheses to the third power. Hit graph. Remember, that's what a cubic looks like. We call this a cubic. And let's clear it out. Okay, not too shabby. Continuing in the realm of review material, if you would, I want to talk about functions, these equations as functions. Remember what a function is? It was a formula that assigns to each value of x one and only one value of y. And it's read f of x. That's what y is, f of x. Give you an example. F of x equals 3x minus 5. Now, earlier you said y equals 3x minus 5. We're going to say f of x equals 3x minus 5. We may have a cost function, c of x, that equals 500 plus 120x. Or another function, g of, in this case, n. Okay? Now, why do we have these? Why don't we just say y and x? Well, this way, you know, you're not going to be able to have a red function, a green function, and a purple function. We're going to have something that differentiates one from the other. And this way we'll be able to say it's f of x or c of x or g of x, or you could even vary the independent variable, the x. We can make it n. Okay, so this way you can talk about more than one function at a time, you see, without using crayons and different colors. One very important concept we're going to be talking about in relation to functions in this course.
Do you mind telling me what this is all about, mister?
Is going to be the domain of a function. The domain, the set of permissible values of the input variable, usually the x, to which a function rule is defined to apply. So it's going to be what's going to be applicable, the part of the function that's going to be applicable to us. Let me see if I can give you an example.
Allow me to demonstrate.
I remember when I was young, we used to always do the annual Chesapeake Bay Bridge walk. Now, if you've ever been on the bridge in a car or walking, the bridge at its lowest height is 20 feet, right where it meets the land, is 20 feet above the surface of the bay. And in the middle, the highest it gets is 120 feet, about 120 feet above the water. And we used to be able to estimate exactly how high above the water we were at any time using our famous spit height function. This is the spit height function. Function h of t. H being how high above the water you are. It's a function h of t time in seconds it took your spit to hit the water. For instance, if I spit And it took 5 seconds. I looked over and I counted 5 seconds for my spit to hit the water. Well, let's see what this is, what this function tells me, the height above the water that I am. I do what's in parentheses, 10 minus 5. That's 5. Let's see, do my exponent. 5 squared is 25, and 120 minus 25, well, if it takes 5 seconds, I guess I'm 95 feet above the bay. And that's a pretty good estimate. Do another. If it takes 10 seconds, took 10 seconds, that's a long time. It takes 10 seconds for the spit to hit the bay. Well, let's see, 10 minus 10, do that's in parentheses first, is 0, right? And 0 squared is 0, so 120 minus 0 is 120. If I waited the full 10 seconds, I must be at the highest point of the bay. That's 120 feet. I know that's the highest point. Okay, so if it takes 10 seconds, I'm probably right in the middle of the bridge. Now, the function only works for certain numbers, actually. Okay, because at more than 10 seconds, well, the spit's just sitting there in the water already, okay? So it doesn't make any sense above 10 seconds. And if you think about it, it doesn't make any sense for below 0. I mean, there's no such thing as negative. Well, there is negative seconds, but at 0 seconds, it's still in my mouth. So that it would be stupid to talk about anything lower than 0, okay? So the domain of this function, I hope you appreciate, what makes it applicable is the set of t values, t for time, where t is more than 0. It's not even useful if it's equal to 0, is it? And less than or equal to 10. Any more than 10 and it's of no use. So the domain is t between 0 and 10. That's some example of domain, if you get the idea. Why would we talk about domain? Well, not only what makes it applicable to us, but there's going to be some no-nos in math that we're going to want to stay away from, of course. For instance, in this, what kind of numbers would you want to put in for x? Or what kind of numbers would you not want to put in for x, you might add?
Now what am I gonna do?
Well, I can't let the denominator be 0. So a typical domain in a fraction is something like any x as long as x, in this case, as long as x isn't 2, as long as it doesn't make the denominator equal to 0. That's a typical domain to keep you out of trouble. I'll give you another example. What about with square roots? Well, square roots,
Yes, you're in deep doo now.
they don't make any sense if you're trying to take the square root of a negative number. So we can't let what's inside that radical sign be negative. So x is going to have to be more than negative 3. Otherwise, it's going to be a negative number, and we're not going to know what's going on. Okay? So that's kind of an example of domains keeping you away from mathematical no-nos.
I demand an explanation.
The most important reason for discussing these, however,
Ha! Just as I suspected.
is to isolate what part of the problem is actually usefully practical to us. Okay? Because that's the whole deal in this course now, remember, is to make this thing useful to us. Consider the function n of p. Okay, it's something we're doing to p. N, well, p is going to be the selling price of a CD by Mr. William Hung. You may have heard of him. He's not that good, but some people like to buy it for people as a joke. So you're trying to sell this thing, and you're going to set the price, p. Okay, and n is going to measure. N's going to measure the number of CDs sold in thousands. Okay? Now let's think. If we put in 0 for P, in other words, if the price is 0, you're giving it away. Okay? This function is going to be, now this is in thousands, the function is going to report 81. We're going to sell, kind of sell, we're going to give away 81,000 CDs. Okay, I can believe that. Now, as soon as we raise the price to $5, the function is going to return 81 minus 5 squared, or 81 minus 25, or 56,000 CDs. We're going to sell less because we raised the price, aren't we? What if we raise the price to $9? What if we get greedy? Okay, well, let's see. 81 minus 9 squared, 81 minus 81 Well, if we raise the price to $9, you can believe that that's a little too expensive as a joke. No one's going to buy this CD. He's not that good a singer, as you know. Okay? So anything above 9 isn't going to make any sense. So here's another case where we're going to use a domain. And in fact, if you put a number above 9, like 10, what's that going to be? We're going to sell, well, that doesn't make any sense. We're going to sell negative 19,000 CDs. So anything above 9, even 10, is not going to make any sense. Okay? So in this problem, we could say that we're only interested in the numbers or the prices between 0 and 9. Those are the only ones that could even make any sense at all. Get the idea? And we would want to limit it to those. Now we can limit those looking at this function, the graph of this function. We can actually limit them on a calculator, the numbers that we put in. We do that using window, the window button. Now if you hit window, these are the options you'll get. Since we're limiting in the domain, we're limiting the x for this function. If you hit y equals, clear out the old one, and type in the function using your x button, and graph it, okay, you'll see the whole thing. And let's do that. Let me get this calculator. And I got to turn mine on because it came off. Okay, let's see. I'm going to hit y equals, clear out the old one, and I'm going to put 81 minus x to the second. And I'm going to take a look at this by hitting the graph button. Now that's the whole graph. Goes all the way up to 81. You see these, each of these little clickers here, units. It's going to go up to 81. It's going to be very difficult to read. And remember, I was only interested in the numbers from 0 to 9. So now what do? Well, I'll tell you what. I'm going to limit the domain of this function on the, or the picture of this function on the calculator using window. Now remember, the domain is from 0 to 9. So when I hit window, I want to talk about limiting the x value from 0 to 9. I'm going to change the minimum x value and the maximum x value. Okay? And then I'm going to try and limit the range. I'm going to limit the y value and make it go from 0 to 81, because those are the only numbers I'm interested there. That's as high as it'll get. I figured that out already. So let's try that with the calculator. 0 to 9 as far as my x's, and 0 to 81 as far as my y's. Let's see. I'll hit window, and I'm going to make this a 0, this x min. So I'll type 0, and then I'll go down and make the x max 9, and then I'll go down, and I'm not going to change the x scale. Okay, I'm going to make the y minimum value a 0, and I'm going to go down, and I'm going to make the y maximum value an 81. And I'm not going to change anything else, so I'm going to hit graph, and look how nicely it kind of centers everything I want to know on this graph. Very nicely. Now the scales are different, okay, and I might have to play with that later, but the point is the means whereby I'm going to manipulate the domain and the range visually on this graphing calculator is going to be in the Windows setting. Now if I look at window, everything's all different. If I want to do a different problem and set it back to the way it was, you know, start off back in the standard window, well, what am I going to do? Well, I'll tell you. Probably the easiest way to get it back to a standard window to do another problem is to use the zoom button. Remember the zoom button? Well, maybe if you don't. that's what I use it for. There's zoom. If you hit zoom, it's going to give you 7 options. Zoom out, zoom in. But if you hit 6, zoom standard, it'll get back to the default window.
I'll be back.
And remember what the default window is between -10 and 10 for X and for Y. Okay? Let me show you how you do that. Bring up the TI. And let's see. Right now it's looking like that. But if I go zoom, standard, which is 6, I can either cursor down to 6 or just, I'm too lazy, I'll hit a 6. Now I can see I'm back to the standard, which wasn't very useful in this problem, but it will be perhaps in the next one. Okay, so let's clear it out and we're ready to boogie. Why should we cover functions anyway? Well, the value of function equations is they're going to allow you, once you have that magic formula, okay, we're going to be working to get the formula, but once you can get that magic formula, you're going to be able to predict stuff. You're going to be able to convert stuff. You're going to be able to do all kinds of, for instance, we can convert units between Fahrenheit and centigrade that's used in chemistry and physics. 0 degrees centigrade, you can put it into the function. Let's see, 9/5 times 0 plus 32. You know the answer to that. 32 degrees. But you can put other temperatures in.
Next.
What if I put in 25 degrees centigrade? Okay, I can tell you the Fahrenheit version of that. Let's see. The 5 is going to cancel with the 25, and I'll get 5 times 9 is 45 plus 32. And I know it's 77 degrees. I could use the function to do that, you see. I may have a function to make predictions in sales or for enrollments at schools or whatever. Okay, here's an example. S of t. Well, t usually stands for time. After 2 years, hopefully you'll be able to tell me what number of people would be perhaps at this university, we'll say. How many students, S students after 2 years? Well, I'll put in a 2. And 5,000 times 2 plus 100,000, well, that function can be useful. It can tell me in 2 years, the future, I'm going to have 110,000 students.
Next.
I can use it for all kinds of numbers. So let's put in a 10. Put in a 10 for time. 5,000 times 10 is 50,000 plus 100,000. Apparently after 10 years, the function will predict that I'm going to have 150,000 students. Okay, I get another example. And you use this on your tax form. You can estimate how much your automobile is worth, or your home, or whatever. It's called depreciation over time. This is the value, or V, value function over time. I wonder how much my dream car, $25,000 car, is worth, say, after 5 years. Well, let's put in 5 for T. 25,000 minus 3,000 times 5, or 25,000 minus 15,000. After 5 years, that car is worth about $10,000, and that seems right.
Next.
After 8 years, let's put in 8. 25,000 minus 3,000 times 8, or 24,000. 25 minus 24. After 8 years, that car is only worth $1,000. Okay, you get the kind of uses, hopefully, for these formulas. Now, they're going to be of great use if you have the formula. The hard part is getting the Dadburn formula. There's going to be clues to finding these equations, these formulas.
Here's someone who can help you.
A linear equation will always be of the form y equals mx plus b, where m is the slope and b is the y-intercept. You remember that? For instance, y equals minus 2x plus 7. Minus 2 is the slope and 7 is the y-intercept.
Whoa!
Now, it doesn't matter what order they're in. Don't forget, the number in front of x is the slope. So in this case, the slope is 3. And the constant by itself, in this case minus 5, is the y-intercept.
Yoink.
What about this one? Well, that one has a slope of 0 because it's the number in front of x, and there isn't an x. and the y-intercept is 15.
But that's so easy. I should have thought of it for you.
It's not that bad, is it? This one has a slope of 3/5. What is the y-intercept? The number sitting by itself. Well, it's not there, so that one's 0. Okay? So it always works.
What would you do with a brain if you had one?
Well, if I give you a picture, you should be able to find at least the slope of this and the y-intercept if you remember what they mean. The slope is measured by between any 2 points, and I picked easy ones, the amount you go up, called the rise, divided by the amount you go over, called the run. In this case, I went up 3 between these 2 points. I went up 3 and over 1. The slope is 3/1, or 3. Now this red line isn't going to have as high a number for the slope because it's not as steep. Let me pick 2 points, and the rise would be 1 perhaps, and the run would be how many blocks? 2. So the slope in this, shouldn't surprise you, is a lower number, 1/2, or a half.
Okay, see now, what I just heard? Blah, 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 blah.
Okay, let's do it again. Because there's a formula we can use. We don't have to draw a picture every time. If say the first point, I just picked any point, was 0, 2, and the second point was 3, 4. The amount you went up is really a subtraction of the 2 y values. In this case, y, we call it y sub 2 minus y sub 1, or in this case 4 minus 2. That's the rise. I don't even need a picture. And the run would be, even if you didn't have a picture, a subtraction of the x values, or x sub 2 minus x sub 1. 3 minus 0. And we could calculate this and find the slope between these 2 points without even drawing the picture. 4 minus 2 is 2. 3 minus 0 is 3. And in fact, the slope of this line, looking at it, is 2/3.
Now then, boy, we'll see how much you learn.
Well, remember what our goal was to find this formula, find the equation.
Excuse me, Professor Brainiac.
Suppose I asked you to find an equation of a line that goes through the point 2,5 and had a slope of -2. Well, we know it's always of the form y equals something times x plus something. Let's put the slope in right away. We're halfway there. The other thing we do is take that point, and we know it fits because it's on the line. And then we know that 2 is the x and 5 is the y. So let me put in for x a 2 and for y a 5 and find out what b, or the y-intercept, is. It will have to be, if you would. Well, -4 plus b is 5. Let's solve for b. Who's keeping b from being alone? The -4. We add 4 to both sides. And in this case, b must be 9. So I'll put it in. And guess what?
How sweet it is.
I've got the formula. You'll always be looking for formulas because you can use them to predict things, you see.
Oh, man.
Let's do another one. I want a line, the equation of the line that goes through these 2 points. Okay? Well, I can get the slope using that slope formula. y1 minus y2 over x1 minus x2. So let's put them in. Okay, we actually do the calculation. I get 6 over -3, or the slope is -2. Now, where do I put that? Remember, that always goes in front of the x. Now, how do I find out the b, or y-intercept? Well, I pick one of the points. It really doesn't matter which one. And I put in the first number for the x and the second number for the y. I'll just pick the first point, 2, -1. I put in the 2 for the x and the -1 for the y. And I have to solve for b. So in this case, I'll have to add a 4 to both sides. And I'll get b is 3. 4 plus -1. And once I know what b is, I put it in, and I have
Genius.
my formula.
Sheer genius.
Okay? I'm going to have a lot of these in the homework, so let's do one more.
respect, sir. I believe this is going to be our finest hour.
I think we can do it. We'll review everything. The x-intercept is 3, and the y-intercept is -2. That's kind of a screwy clue, isn't it? Well, if the x-intercept is 3, that means the point 3, 0 is on there. And if the y-intercept is -2, that means the point 0, -2 is on there. Remember what it means to be the x-intercept and y-intercept. Okay? Once we have those 2 points,
Hey, that's just crazy enough to work.
I can use my slope formula again. y1 minus y2 over x1 minus x2. And guess what I get? 2/3. So let's put that here for the slope. And now they're all the same. I'm going to pick either point, and these are easy points. Pick either point to put in for x and y. If I put in the 3, 0, the 3's will cancel. I love that. And it looks like b's going to have to be a -2. And I'll put that in. And it doesn't get much harder than that. And once you've found that formula, we're going to be able to use it. Well, I'll be showing you later what we're going to use these kind of formulas for, these functions, if you would. Now, let's talk about working with 2 at the same time. If we look at 2 lines at the same time, really 2 type of things can happen. One is that they can be, what do you call those lines? They can be parallel. Or, if they're not parallel, what happens? They intersect, meaning they touch. That's going to be of great use to us because we're going to like the ones that touch.
What happened?
Well, let's see if you can figure out without a picture whether these are parallel or intersect. Well, the key is, let's solve them both for y, and I bet you'll get the idea. Solving this one for y, subtracting the 6x from both sides, and then dividing by 2, I get y is 4 minus 3x. If I solve the other one for y, I divide by 4, and I get y equals 2 minus 3x. Well, these 2 equations, remember where the slope is, they have the same slope, but different y-intercepts. So they lean the same way. They have the same slope, but they're not the same line. They're parallel. Anytime 2 equations have the same slope, the same number in front of x, they are parallel. Let's do it again. 2 more lines. Always begin by solving for y. In this case, all I have to do is divide by 2. And in this one, let's see, I'll have to subtract 10x and divide by 4. Now these ones, they have different slopes. The number in front of x is different. And as soon as 2 lines have different slopes, you know they have to touch. They have to intersect. So that's not that bad.
Now I say look at here.
Remember, when things intersect, they look kind of like that. But they could also intersect at a 90-degree angle. Remember what that is? Lines are perpendicular when they intersect.
Well, isn't that special?
When they intersect at a 90-degree angle, we call them perpendicular. And a lot of things in construction are perpendicular. We'd like to know algebraically when they're perpendicular. That's going to occur when one of them has a slope of a over b, and the other one has a negative reciprocal of that, a slope of negative b over a.
How about little fires, Scarecrow?
Let's try doing some. Let's look at these 2. They're both solved for y. Well, do they intersect?
Yes.
Because their slopes are different. Are they perpendicular? Well, one's 2 and one's -3. No, they're not. Let's look at this one. Do they intersect? Are their slopes different?
Yes.
Are they perpendicular? Are they the negative reciprocals of each other?
Woohoo.
There you go. You can see minus 3 over 2 and positive 2 over 3. So they are perpendicular. There's another couple. They are intersecting
Yes!
because the slopes are different. And in this case, once again, they are perpendicular. One is the negative reciprocal of the other, 5/7 and negative 7/5. Now this is a little bit tricky. Do these ones intersect?
Nothing for you.
They're not even intersect. They're parallel because the slopes are the same, you see? Do these ones intersect?
Yes!
They intersect because the slopes are different. Now this is tricky. Minus 3, don't forget, is minus 3 over 1. And the other slope is 1 over 3. So in this case, it might not look right away. They are perpendicular. Let's do one more. Well, 7 and 9,
Yes!
they're going to intersect. But they're not going to be perpendicular. Okay?
Boring.
Yeah. Okay, you get the idea? Let's get back to our function search.
Oh, I can't take it anymore.
With a couple more clues, different clues if you would.
Not because they are easy, but because they are hard.
The more difficult they get, the more useful they will become, I promise you. I need a linear equation of a line that is perpendicular to y minus 3x equals 7 and also runs through the point 3, 5. Well, let's see. Let's solve that for y. Because we don't know anything until we do that.
Hassan Chop.
And I get y is 7 plus 3x. Now, if the line that I want is perpendicular to that line, the original line has a slope of 3 over 1. So the line perpendicular to that would have a negative reciprocal.
Well, ooh-la-dee-da.
Remember?
I'm dangerous. I'm very, very dangerous.
So its slope's going to have to be negative 1 over 3. Now all I got to do is make 3, 5 fit in there. Well, let's write that equation and put the 3 in for x and the 5 in for y and make b fit. Well, let's see, the 3's will nicely cancel.
Hassan Chop.
And I'll get 5 is negative 1 plus b. I'll have to solve for b by adding 1. And b will be 6. And there it is. It wasn't that bad.
You are correct, sir.
Okay. I can see that it works.
Thank you, sir. May I have another?
That was tough. We'll do another.
My poor will queen.
This time I want a line that's parallel to this y minus 5x equals negative 8 and runs through another point. Well, parallel means they have the same slope. But I don't know anything until what? Until I solve for y. So I got to add 5x.
Hassan Chop.
And I get y is 5x minus 8. Now what's the slope of this line, 5x minus 8? Well, 5. And I know my desired line is parallel to that, so it'll have the same slope.
Oh, yes.
Remember that, okay? So I can just throw a 5 in there. Don't have to do the fancy perpendicular stuff. Now all I got to do is make 3, 7 fit. Okay, I'll put a 3 in for x and a 7 for y. And I get 15 plus something is 7. Let's solve. And I get b.
Hassan Chop.
B must be negative 8. And there it is. Okay?
We can't do it. If we keep this speed, we'll blow up any minute now.
I can do it. Hang it. One more. We need a line that goes through these points. Remember your slope formula. y1 minus y2 over x1 minus x2. And I get a nice fat 3. This was an easy one, wasn't it? And then how do I get the y-intercept, the b? Well, pick easy point with either point, really. I picked the 1, 4 because the numbers were lower. Okay, and b in this case, solving must be a 1. You got it, bub.
I have a feeling, sir, bad stuff is about to go down.
Okay, now we've done the hard part, the math stuff. Let's reap the benefits and do the applications of these linear functions. Some of the useful, practical applications that we know. You ready?
And now, ladies and gentlemen, let's get ready to rumble!
Let's just talk about something as basic as temperature. We've done it before.
There's something I have to ask you.
What are the freezing temperatures at Fahrenheit and at centigrade? I bet you know one of them. Now, you know 32 degrees is freezing for Fahrenheit. Do you know what the freezing temperature for centigrade is? Well, it's 0, okay? You know what the boiling temperature for Fahrenheit is? Okay, if you took your science, you know it's 212 Fahrenheit. What is the boiling temperature for centigrade? Centigrade's much easier to work with. That's what everybody wants us to go metric. Anyway, we have really 2 pairs here. And if we have 2 pairs, remember, 2 points, we could actually come up with a function that allow us to predict every other point. This is going to be useful, at least in science it is. I'm going to actually find a function that allows me to predict the Fahrenheit temperature based on the centigrade, or vice versa. Let's see if we can do it. Well, I have the 2 points. Let's use our slope formula. y2 minus y1 over x2 minus x1. What does it come out to? 212 minus 32 over 100 minus 0. 180 minus 100. Let's reduce that. That's 9/5. Okay, that goes there. Now remember what we did. We did this a couple times. Let's pick any point. I'm picking the easy one. Remember, you love 0. And put it in. And let's see what b has to be. Well, 0 nicely knocks everything out. And b has to be 32. And how cool is that? That, in fact, is the function of Fahrenheit versus centigrade. And why do you care? Because you can actually use it. If I gave you 20 degrees centigrade, you could tell me the Fahrenheit temperature. Put in a 20. Let's see. 20 over 5, 4 times 9. I'd have to reduce. And 36 plus 32.
Hey, this is great, man!
You can see that I could pick any point, any temperature centigrade, and tell you the temperature at Fahrenheit.
It's not the principle of the thing, it's the money.
How about if you opened a company? You're going to want to use a cost function. Okay? We're going to call it C just because it's cost function. Okay? And we're going to buy ourselves a sausage stuffing machine. That costs $1,200 just to get the darn machine. Okay? Startup costs, if you would. Okay? Or we call that fixed cost because it's a one-shot deal and there's nothing you can do about it. Now add to that the ingredients for each sausage. Now that's not fixed because depending on how many sausages you make, you make a lot, it's going to cost you a lot, kind of a thing. You make not that many, it's not going to cost you that many, kind of a thing. Okay, we're going to say that it cost me 32 cents for just the ingredients of the sausage. Okay, X being the number of sausages. So we're going to have a fancy word for that, the direct costs or the marginal costs. Okay? So our cost function in this case of making sausages is going to be the fixed plus the marginal, 1,200 plus 32 cents times X, or 0.32 times X. And we can use it to predict the costs of, however, depending on how many sausages we make. If we make one sausage, you bought all that equipment and for one sausage, now let's put a 1 in. You see that one individual sausage is going to cost you
What a chip.
$1,200. That's an expensive sausage. $1,200.32. Well, that's not going to make any sense, is it? What would the cost of 1,000 sausages be? Well, let's put 1,000 in for x. 1,200 plus 0.32 times 1,000. It's going to come out to $1,520. Big deal. Well, if we divide that by 1,000, we'll find out how much each individual sausage cost us.
Yes!
Each individual, at that rate, if I made 1,000, it would cost me $1.52 for each sausage.
Hey, wait just a minute.
Well, now I'm thinking, wait a minute. Instead of making 1,000, let me make 10,000. See what happens. Put in 10,000. It's going to cost me a lot. It's going to cost me $4,400. But for each sausage, let's divide by 10,000. What's 4,400 divided by 10,000? If I make that many sausages, I'm looking at 44 cents a sausage. Well, now I could sell it for more than that, and I could make some money.
Well, duh.
So you might think the more you make, the cheaper they are to make. And that's how you make money, of course, in bulk. And this is now we're starting to smell the function, the uses of function in business. I hope you are. Let's look at one very last use today of functions. Montgomery College Germantown campus had an enrollment of 12,000 in the year Y2K in 2000. And I know that we've experienced a growth of 600 students because of all the townhouses and houses being built around here every year since. Now, if we had a function, we could predict future enrollment. That would be of great use to us. We could predict future enrollment, and I'm going to expect you to be able to do something like that. Predict the future maybe in 2010. And even use that function backwards to tell me how many years it'll take till we have a 20,000 enrollment, till we're a huge school. Okay? What would we do?
Perhaps I could be of some assistance.
Well, I'm going to give you an enrollment function here. The fixed number we got from the word problem up there is 12,000. That's what we started with. Okay? And then for every year, is going to be 600. So it's going to be 12,000 plus 600x. You have to be able to come up with that function given the verbiage that they give you here. Now, let's predict that in the year 2010. We're not going to put the number 2010 in, are we? We're going to put in the number of years since 2000, which in that year will be a 10. So enrollment using the number 10 will be, let's see, 12,000 plus 600 times 10, 18,000. We're going to be way up there in 2010. Now, I wonder when we'll be at 20,000. Well, 20,000 is the answer. That's the actual enrollment. So we're not going to put that in for x in this case. We're going to put that in for the e of x. It used to be called y, didn't it? Now, then we'll solve for the number to put in. How are we going to solve? I'll subtract the fixed value, the constant 12,000 from both sides, and then divide by the marginal value, 600.
You're absolutely correct.
And you can get it right out there. In 13.33 years, we will be at an enrollment of 20,000. That's going to be of great use to us to to prepare for that. Well,
Thank you very much for joining us tonight. We'll see you tomorrow. Good night, everybody.
that's enough for today. We'll see you next time. Aloha.